Hi everyone, thanks for joining to another Australian fluid mechanics seminar series. It's my pleasure to introduce today's speaker, Dr. Sean Symon. He studied aerospace engineering at University of Maryland, and he did his PhD at California Institute of Technology under supervision of Professor Beverly McLean. And Sean was a postdoc at Melbourne University for 2 years before he started his journey as a lecturer recently at University of Southampton. And he's going to give us the talk today on nonlinearity, the Frenemy of the linearized Navier-Stokes analysis. Thank you.
Thanks very much, Ram, and thanks, Kat, also for helping get the seminar organized. Can you see my screen?
Yes.
Excellent. Okay. And I also have to thank Julio for the invitation. Yeah, so today's talk is going to be work I did with collaborators at the University of Melbourne, where I was a postdoc. So my supervisors were Simon Illingworth and Ivan Marusik. And I also worked with PhD students Bojin and Anaga Madhusudanan. And some of this work I also did in collaboration with my PhD supervisor, Beverly McKeon, and my friend from Caltech, Kevin Rosenberg. And the last person on this list is Denny Sip from Onera. So hopefully that gives you a slight idea of the flavor of this talk. And I've sort of come up with this ridiculous title where I've called Nonlinearity the Frenemy. And the reason I've called it the Frenemy is sometimes it actually helps us figure out what's going on, and sometimes it makes life really difficult. So I'm going to start this talk with, whoops, I cannot seem to, there we go. Show you some pictures, and I'm going to be comparing structures for my favorite flow, which is flow around a circular cylinder. And it's my favorite flow because it's like the Giving Tree, if you've ever read that book back when you were 6 years old. And the Giving Tree gives a little boy all its apples to begin with, and then the boy comes back and the tree gives its branches, and then the boy comes back again and the tree gives its trunk, and after that the Giving Tree says to the boy, I have nothing left to give you. Now, cylinder flow for me is like the Giving Tree, but it keeps regerminating, much to my happiness. And every time I come back to it, it sort of sheds light for me on some of these complex tools that we tend to use in the fluid mechanics community. So each time I come back to cylinder flow and look at it again in some different lights, I learn something new from it. And I'm going to be trying to show you something that you've probably seen already in many other very complicated flows, but I'm going to show it to you in the context of a cylinder flow to try and work out what's going on. So the first set of structures here are from the linearized Navier-Stokes equations. So you can get these either from a stability analysis using the mean as your reference state, or you can also get it from resolvent analysis. Resolvent analysis just gives you the exact same thing as the stability analysis does. And you see a nice, beautiful vortex shedding mode, which is not particularly remarkable. What is remarkable that Dwight Barclay found was that the eigenvalue for this flow has a real part of 0, and the imaginary part of the eigenvalue gives you the shedding frequency, which is perhaps somewhat surprising because when you linearize around the base flow, it does not give you the shedding frequency. So that means that there's some information encoded in the mean velocity field that the linearized Navier-Stokes equations is able to pick out with great success. Now, as great as these structures are, I'm now showing you what you would get from data. So what I mean by that is if you had DNS data or data from an experiment and you Fourier transformed this data in time, you can extract the true Fourier mode. And this is a deterministic flow, so you can get a Fourier mode that represents this vortex shedding perfectly. And what I want to draw your attention to, this is the Streamwise velocity component on the left, are the differences between these two structures. So for the linearized Navier-Stokes equations, if I just focus on this blue contour here, I see 4 different contour levels. And if I look at the data version, I only see 2 different contour levels. So already I'm about a factor of 2 off, and I'm not even 6 diameters behind the cylinder. So despite how accurate the structure looks on the surface, there are some very important differences. And I'm going to try and discuss why that's significant in the context of both this flow and more complicated flows. So this is going to be the outline of the talk. There are going to be 3 parts, sort of increasing complexity in terms of the flow that we're studying. So you don't have to worry about what these pictures mean yet. So I'm going to explain them to you. And my conclusion slide is quite literally the exact same as this outline slide. And we're first going to just look at a cylinder flow where we're going to deal with nonlinearity explicitly. So it's a very simple flow. It's pretty easy to calculate nonlinear terms. And I'm going to be able to do that and analyze how the nonlinearity interacts with the linearized Navier-Stokes equations. The second part of the talk is going to be dealing with an exact coherent structure. So an exact coherent structure is a solution of the Navier-Stokes equations, and it has some properties that are similar to a turbulent flow. But the advantage of the exact coherent structure is, like the cylinder, it's a deterministic, let's call it deterministic entity, so to speak. And we can compare the nonlinearity in the context of nonlinear transfer, so that's what this is, with how well an eddy viscosity is able to model that. So at the end of this talk, you'll understand what these 3 figures are, hopefully. And then the last part of the talk is going to deal with the most complicated flow. This is turbulent channel flow at a friction Reynolds number of 2000. So there's, I guess, having dealt with high Reynolds number turbulence at the University of Melbourne, 2000 is kind of a baby Reynolds number, but it has some resemblance of a log region. And we're going to take a look at how we can guesstimate, so to speak, nonlinearity for this flow, and then use that to build a linear estimator of the flow. So the thread tying these 3 flows together is basically how explicitly we're dealing with nonlinearity. So we deal with it very explicitly at the beginning, then we attempt to model it, and then we attempt to use data to give us some prediction of what it looks like, just as a means to an end, really. So part 1 is the cylinder flow, and I'm going to start in a very bizarre way. So I'm going to start with a result that came out of the Colonius group, actually, and you heard Tim speak last week, and this was his PhD student, Aaron Town, who's now an assistant professor at the University of Michigan. And I'm going to start with a result that they derived in their paper, and this compares resolvent analysis, so this is the linearized Navier-Stokes equations, to SPOD, and this is basically a data-driven decomposition. And this stands for spectral proper orthogonal decomposition. And it's kind of POD in the frequency domain. So if you know what POD is, if you were to just Fourier transform things before you did POD, that's basically what SPOD is. So I'm going to start with a relationship between the velocity field, and this is the velocity field in Fourier space, that's why it's a function of omega, and the nonlinear forcing. So the nonlinear forcing is going to be this F, and it's also in the Fourier space with omega. And there is a linear operator that maps the nonlinear forcing to the velocity. So that's what this equation means. Now, what I've assumed here is I've assumed that after Fourier transformed the flow and got some sort of structure for this frequency, I'm assuming that, for example, if I take data on Monday, I might get a Fourier mode for Monday. And if I come back and take a bunch of data and do a Fourier transform on Tuesday, if my structure is basically the same, that means that I have a deterministic flow, like cylinder flow, and that I have the same Fourier mode. But what happens for more complicated flows is I might actually get some subtle differences between my Monday data set and my Tuesday data sets. And in fact, if I come back Wednesday, Thursday, Friday, and if this is a turbulent flow at high Reynolds number, all 5 of those Fourier modes might have some differences between them. And what SPOD is trying to do is it's trying to extract for each of those frequencies what is the structure that's common between all 5 of those data sets. And what you're hoping is that one structure can capture most of the statistical variance that you see in each of those 5 samples. So the way we do that in practice is we get a bunch of Fourier modes and we form a matrix by multiplying this equation by its complex conjugate I should say. And here I can combine this into a matrix, which is the cross-spectral density matrix of the velocity. That sounds intimidating, but all it just means is I have a matrix where I've multiplied these out together, and I get a similar matrix for the nonlinear forcing. Now, what's often done is that we assume that, so nonlinearity is quite difficult to calculate, especially from an experiment. So if you think about a turbulent flow, most people measure that with planar PIV or stereo PIV, and it's difficult to compute the nonlinear field with that field of view. So one of the assumptions we can make to try and make life a little bit easier is we substitute the identity matrix for the nonlinear forcing statistics. This is what we refer to as white noise. And we can analyze the linear operator using this singular value decomposition that you would use in POD, actually. The only difference being that this operator comes from the equations. So you get velocity structures, and they have some sort of amplification factor called sigma, and phi just is the initial condition, so to speak, that would give you that velocity structure. Now, what you can do is you can actually find a nice equivalence between SPOD and Resolvent if you use this white forcing assumption, because what you'll notice is when we substitute an I here and we plug in the single value decomposition for H, we actually get a very nice expression for Resolvent modes where we have a psi sigma squared psi star. And this looks basically the same as what happens if you eigen-decompose your cross-spectral density matrix. You get a V lambda V inverse. And this you can do actually from PIV data, simulation data relatively easily once you've constructed your snapshots, you Fourier transformed, you formed your matrix, and then you eigen-decompose it. And so what this means is that SPOD modes will be the same as Resolvent modes if this forcing is white noise. So a lot of this talk is going to focus on how good is that assumption. So I'm now showing you plots that my collaborator Bo generated. And this is the power spectrum of cylinder flow, which you've probably seen many times. And what's very nice about this flow is that you have a dominant shedding frequency, and due to the nonlinear interactions in the flow, you also see peaks at harmonics of this shedding frequency. Now, resolvent analysis, you only see one peak. So what I'm plotting here is the most amplified structure. And what's, I guess, more interesting is what's missing. So I'm missing a lot of different peaks after the shedding frequency. And if my nonlinear forcing is white noise, that means my SPOD eigenvalues should also have the same behavior as the resolvent. But what we notice, and I apologize for the lousy frequency resolution, SPOD is a very data greedy algorithm, and I was very cheap. That's why you see pretty poor frequency resolution. So I really should have probably had 10,000 snapshots rather than the 1,000 I used. But this illustrates the point sufficiently. And that is that you do have a nice clear peak at the shedding frequency, of course, and that peak is quite dominant. But you also have peaks at all harmonics. And not only do you have peaks, but really all the energy is contained in the first eigenvalue for all of these modes. And that's not true for resolvent analysis, as I'll show you in a moment. So that means that we're going to have to reassess this white noise forcing that we originally assumed for our nonlinear terms. So just to reinforce what happens, so this is the shedding frequency again, a comparison between let's just call this resolvent, but you get the same for stability analysis and data, we get a decent first order approximation, of course, but they're not the same. And if we were to look now at the second harmonic of the shedding frequency, okay, the resolvent doesn't show any mechanism. So the resolvent is basically throwing its hands up in the air and saying, I can't help you here. I don't see a linear amplification mechanism. I don't see the mean flow giving rise to this fluctuation. Therefore, I'm warning you, I'm probably going to give you garbage. And that's exactly what it does give us. It gives us this free stream mode that's not even in the cylinder wake. And if you were to compare that to the truth, that's what these SPOD modes are. DMD would give you the exact same thing for this flow. You see that this is a very nice structure that's basically concentrated in the cylinder wake, and that has absolutely no resemblance to what the resolvent gives you. So this is where you have to start dealing with some explicit treatment of the nonlinearity here if you want to try and get this structure correct. So this is the resolvent norm now, and I've plotted both sigma 1 and sigma 2, so you can see that there's a very sharp peak at the shedding frequency, and then above 1.5, both singular values are in essence the exact same value. And what we observed from SPOD was that the rank of this matrix is about 1. So why am I saying that? Well, if I go back to my SPOD results, you can see that the bulk of the energy for SPOD happens at a single eigenvalue. So that means that I can represent this frequency pretty accurately with a single SPOD mode. And if I can represent it with a single SPOD mode, that means that the rank of the SUU matrix has to be about 1. So the rank of the SUU matrix is a 1 for basically all these peaks. So that's where that statement comes from. And the rank of the resolvent, meanwhile, well, if I haven't actually plotted the second, I haven't plotted the second harmonic of the shedding frequency, but if I just continued this line, you would see that basically the first 10 singular values at least are all practically the same value. That means that because I have so many sigmas that are the same value, there's absolutely no way I can represent the resolvent as a rank 1 matrix. It's a high rank matrix. So this is at first glance incompatible because I need to have low rank behavior even though the resolvent isn't giving me low rank behavior. So what does that mean? Well, that means that the nonlinear forcing must be low rank in order for the left-hand side to be low rank. And that's completely incompatible with our assumption that this is white noise. And why is that incompatible with our assumption that this is white noise? Well, the identity matrix, the rank of the identity matrix is huge. It's the size of the identity matrix. So if your identity matrix is 50,000 by 50,000, the rank of that matrix is 50,000. And 50,000 is much larger than 1. So we need this to be 1 because the rank of the left-hand side is basically the minimum between the rank of either the resolvent, and we know that the resolvent is high rank based on these singular values, even though I've been lazy and I've only plotted 2. And it's the minimum between that and the minimum between the rank of the nonlinear forcing. So this basically tells us that the rank of the nonlinear forcing has to be about 1. And that's the complete opposite of what you assume when you have white noise. So if we can now actually plot the SPOD eigenvalues for the nonlinear forcing. So if you do that, you see once again that there's a very big gap now between the first eigenvalue and the second eigenvalue for the shedding frequency and all of its harmonics. And if I hadn't been lazy and if I had actually done SPOD for 10,000 snapshots rather than 1,000, you would probably see that these eigenvalues both converge to very, very small values. So they're artificially a bit more energetic than they are in truth, but just because I didn't use enough snapshots for SPOD. So this is a pretty important result because it tells us that really our treatment of the nonlinear forcing as white noise is probably not the right way to go. And another thing to show you is that the shedding frequency is also not white noise. So the nonlinear forcing is also rank 1 for the shedding frequency, even though we assumed that was white noise as well. So that's why you get differences between the structures between SPOD and Resolvent at this frequency. It's because the white noise here is also low rank, or sorry, not the white noise, the nonlinear forcing is also low rank. Okay, so this is when I start playing games with triads, just to show you how you can complete the feedback loop. I should have cited SIP and Lebedev here because this is similar to a weakly nonlinear expansion. So the nonlinear forcing, if you wanted to be very rigorous, is the sum of tons and tons of triads that when you add them together give you the desired frequency. So what we try to do is we try to approximate this expression with a truncated sum. And that truncated sum is then mapped by the resolvent operator to the velocity. So just as an example, I think I sort of said this at Monash one time, when you multiply complex exponentials, or when you multiply exponentials, their exponents add. So the exponent would be omega s for both of these. So if you add 1 plus 1, you get 2. That's why you get 2 on the left-hand side. Very, very complicated maths, as you can see. So that's how we can approximate the nonlinear forcing for 2 omega s. We can also approximate the forcing back to omega s, because we know that it's not really white noise. So if we wanted a better approximation of it, we can then look at the difference between frequencies. So here I have 2 minus 1 and minus 1 plus 2. Both of those add up to 1, and that's consistent with my left-hand side. So this is actually what an eddy viscosity tries to do. So the reason I'm bringing up eddy viscosity is because it's going to come up in the second part of the talk. And the eddy viscosity is trying to model the influence of smaller scales back on the larger scales. So there's backscatter here from a higher frequency structure back onto a lower frequency structure through these nonlinear interactions. And that's exactly what you try to model when you're using an eddy viscosity. So just to try and convince you that this set of triads is good enough, this is the true nonlinear forcing. And you can see that there's a little bit of fuzziness going on. That's to do with the fact that I'm using finite elements, and the gradient operator tends to result in this kind of fuzzy-like behavior. And this is what happens when you interact the second harmonic with minus the first harmonic. You pretty much recover the exact nonlinear forcing for this structure. So you can represent the nonlinear forcing with a very small number of triads for this flow. For most flows, that's probably not going to happen. You're probably going to need to look at least several dozen. But for this flow, you can represent it pretty well with just a single pair. So this is designed to make your eyes bleed a bit. So I warn you, there's a lot, it's a busy slide, but we'll introduce it piece by piece. So we start with our mean. Our mean is necessary for the resolvent because our linear Navier-Stokes analysis uses the mean as the reference state. And this mean gets plugged into a bunch of resolvent operators. It's kind of like a little filing cabinet here. And what we noticed was the single value decomposition gives us a decent approximation of the modes at the shedding frequency, okay? And this red and magenta curve, they interact up here. So here are all our linear interactions. And if we do 1 minus 1, we get 0. And the 0th mode, the 0th frequency, is the mean. So these things give you the Reynolds stress, and the Reynolds stress is what drives the mean velocity field. And we can also look at these modes interacting with themselves, and the interaction of these modes themselves gives you 1 plus 1 for 2 and minus 1 for minus 2. And these feed into these resolvent operators. And because these resolvent operators give us garbage if we use a single value decomposition, we have to try and estimate the forcing. And this is our estimation. This gives us a decent approximation of the velocity field at twice the shedding frequency. And you can probably guess what goes into these blank rows. This is where minus 2 interacts with 1 and 2 interacts with minus 1 to give us the forcing at 1 and minus 1. So this is our self-consistent feedback loop. And this is kind of what's happening to sustain the flow. So what's kind of neat actually is you can see this sort of behavior in experiments as well. It's not just cylinder flow at a Reynolds number of 100. You can actually see this for an airfoil. So this is a Reynolds number of 10,000. And similar to the cylinder flow, the resolvent identifies a single peak at the shedding frequency and nothing at the higher harmonics. Whereas SPOD gives us this low rank deterministic behavior at the shedding frequency and its harmonics that are, and this is absent for the resolvent. So you would have to play these triad games like we did for the cylinder if you wanted to try and recover structure at these frequencies. And I've put this in because I find this quite interesting. This is a recent preprint from the KTH group, and they looked at how well a single pair of SPOD modes could recover the velocity field for turbulent channel flow. And the red is what they get if they run a single pair of SPOD modes through the resolvent, and black is the truth. And you can see that the nonlinear forcing is very well described by a single pair of SPOD modes because you get nearly the right structure for the velocity field when you run that through. And I think this is a very interesting and promising result for low order modeling of turbulent flows, especially this structure here, because you can get that near wall attachment, so to speak, quite accurately. Okay, enough of cylinders. Now let's do something that's a little bit more difficult, and this is an exact coherent state. And I'm first going to show you what this exact coherent state is. So this is something that Park and Graham found. Michael Graham is at the University of Wisconsin. And what an exact coherent state is, it's a nonlinear traveling wave. So this thing is in plane Poisson flow, that's what the P is for. It's an upper branch solution, which means it has turbulence-like features. And this thing travels along at a fixed convection velocity. So in other words, the wave speed, the speed at which this thing moves at, is constant, and the whole structure moves at that speed. And what's really nice about this is that its structure is qualitatively similar to near wall turbulence. So just to reinforce that point, I have plotted here the mean profile for the ECS in blue. So it's this wiggly looking thing here. And I plotted the CES profile, which gives you an approximation of a turbulent mean velocity field at the same Reynolds numbers, so friction Reynolds number of 85. And what you can see is you can see very good agreement. There is a little bit of difference, and the difference happens because in a real turbulent flow, you have a continuum of convection velocities, and that continuum exists from 0 to whatever the centerline velocity is. This exact coherence state, meanwhile, you're enforcing that it all has to travel at the same speed together. So when you do that, that's what kind of gives you this rather wiggly behavior, whereas the continuum of convection velocities means you have a much more smooth profile. And another really nice thing to try and convince you that this is similar to near wall turbulence is that when we look at the kinetic energy of different wave number pairs, the most energetic scale has a streak spacing of 100 wall units. And that's similar to the near wall streaks that you see in a turbulent flow. So I'm going to be showing you a lot of these plots, and basically the intensity of the color and the size, the area of the square is indicative of the magnitude. So we can see that this is the most green and it's the largest. That means it's very big. And fainter colors and smaller squares mean it's smaller values, so it's weaker energetically. So you can see that this structure is energetically quite dominant, but you have some other things appearing in the flow as well. So I suppose I should introduce resolvent analysis, which I must confess I'm kind of tired of doing this, so I'm going to go through it kind of fast. So really the leap that McKee and Sharma made back in 2010 was treating the nonlinear terms as a forcing. And they closed the feedback loop. So that feedback loop I showed you for the cylinder flow, that's kind of the framework that McKee and Sharma envisioned in the context of a turbulent pipe flow, in fact. And you start with the incompressible Reynolds, you start with the incompressible Navier-Stokes equations, and you Reynolds decompose that into mean and fluctuation, just as you do for many other tools. And here it's written such that the nonlinear terms on the right-hand side, linear terms left-hand side. And I kind of want to draw your attention to these terms here. You can see that there's an interaction between the mean flow, which is the zeroth harmonic or the zeroth frequency, the zero wave number pair, and the fluctuations. So the reason that this is linear is because we assume we know the mean velocity field in advance. So if we didn't know that, then this would actually be a nonlinear term, or it wouldn't be a nonlinear term, but it would be difficult to calculate. So there's our forcing, and then we Laplace transform these equations in time and Fourier transform in the streamwise and spanwise directions. And then we set S equal to I omega to give us the frequency response. And then we recover, I showed you for cylinder flow that U equals H times F. And now our H is a function of bold K. And this is what's annoying for a turbulent channel flow. And bold K is a wave number triplet. And that means that we have to not only choose omega, but we have to choose Kx and Ky. Now, the lovely thing about this ECS is that it travels at a fixed convection velocity, and that means that we can actually have a unique omega for every single Kx, Ky pair that we choose. So that's nice. That means that the only things that we really have to worry about are choosing Kx and Ky. We don't have to worry about choosing omega. It's sort of given to us by the phase speed of this structure. Okay. And I'm sorry, this is really disgusting looking equations, but it's going to boil down to a very simple result, I promise. So here I've written the fluctuating equations in index notation, and I integrate this over the volume after multiplying it by ui. This is just to recover the Reynolds-Orr equation. This is just to give you an energy balance for the aggregate flow, and in the aggregate flow, production and dissipation are equal to the time rate of change of kinetic energy. And the nonlinear terms, meanwhile, if you integrate that over the volume, they actually contribute 0 net transfer because they are conservative. So the reason I'm writing out the energy transfer equations is because I'm interested in how resolvent analysis compares. So if you, this is really awful looking, isn't it? If you were to time average and integrate over the channel, we're just going to skip to the next slide and note that P, D, and N balance to be 0. That's a nice, simple result. So that awful looking angle brackets and overlines and terms just boils down to this nice formula here. And we can do the same thing for a wave number triplet. So I'm just going to rush through this because once again, it's rather gross looking. And for the velocity field, I'm actually going to substitute the resolvent modes, and I'm going to assume once again white noise forcing. That's why you don't see any phi's on this side. And when you do that, you get this horrible expression. And this just means that for a resolvent mode, it also has to satisfy the PDN balance. So all I want you to take away from all these horrible equations are the things in the boxes. So PD and N are satisfied for each wave number pair, and also PD and N are satisfied for a wave number triplet for resolvent modes. And just to make our life easier, we're just going to consider for now the first resolvent mode. So I'm going to show you in the next slide PD and N for the ECS computed from the actual simulation, so the actual solution. And I'm going to show you PD and N for the resolvent analysis. Okay, so let's start with production. So red means positive, blue means negative. And similar to the previous plot I showed, if the color is quite intense, that means it's big. And if the color is weak, that means it's small. And what we see here is that, not surprisingly, the mode that has the most production is this streamwise streak. So it has a kx of 0 and a ky of 4. And we see that production is generally positive, but we do have some negative production, which seems a bit weird, but that can happen. This Spanwise-constant mode, for example, has negative production. Now, if I look at the resolvent prediction, it looks decent. So I've normalized it based on this structure. So that's why they are the same. And you can see that it predicts mostly positive production as well. However, this one's a little bit more dominant because you can see it kind of drains out 0.8, whereas 0.8 here is a little bit bigger. So Resolvent tends to do well with production mechanisms, and that's because Resolvent is good at modeling the energy transfer between the mean and fluctuations. Now, dissipation is interesting because the DNS looks quite different. So here I see squares of different sizes, and for Resolvent, I see squares are almost the exact same size as production. So if I just made production blue, I almost get the exact same thing as dissipation. That is not what happens in the DNS. In the DNS, I see that I actually do not have a balance between PD and N for 0, 4. That's why I need nonlinear transfer to sort of balance it out. So if I were to add up the value of each tile for 0, 4, it should add up to 0. Not only that, but all of these tiles in nonlinear transfer should add up to 0. That was a result we got from the Reynolds-Orr equation. So you can see that Resolvent predicts almost 0 nonlinear transfer for every scale, and that is quite significant because this is why you see discrepancies between Resolvent modes and SPOD modes, and that's because there's no mechanism in the Resolvent analysis that allows large scales to transfer its energy to smaller scales. It all just gets stuck in the same wave number pair, and that's why in order to satisfy the balance, Resolvent puts all the negative energy into dissipation. So Resolvent says, okay, I can't balance it with nonlinear transfer, so I'm going to balance it with dissipation, whereas in the true flow fields, you actually have both dissipation and nonlinear transfer getting rid of energy. And of course, this nonlinear transfer passes it on to other scales. So Resolvent doesn't do a very good job modeling nonlinear transfer. How can we maybe help it? And we're just going to look at a crude eddy viscosity profile from SES back in 1958. This was actually for pipe flow, and then it was adapted for channel flow by Reynolds and Tiedemann, I think. And we've triple decomposed Navier-Stokes equations here. And there's our wonderful eddy viscosity profile that we're going to use. And when we add this eddy viscosity profile, our resolvent operator changes. That's why you have a little E here. E just means that there's an eddy viscosity inside it. And you also notice that the right-hand side changes as well. This is no longer the nonlinear forcing. This is a different forcing called D. And that's because we've changed the operator. Therefore, we've changed the meaning of the right-hand side here. So if you were to actually compute the energy dissipated by eddy viscosity, there are two terms that contribute to that, and that's just from the chain rule here. So the first term is an effective Reynolds number that changes as a function of wall height. So that's from the new T term. But if you remember the chain rule back from calculus, the derivative of a product is the first times the derivative of the second plus the second times the derivative of the first. So we also have a derivative of nu T, and that's what this G means. It's a gradient of the eddy viscosity profile, and this can also dissipate or add energy. So what's nice about V is it's guaranteed to be negative like dissipation. However, G, it's not sign definite. I can't tell a priori if it's going to be positive or negative. And so the eddy dissipation, so what we're hoping will model N is V hat plus G hat. And I'm going to call eddy dissipation ed hat. So that's what ed hat looks like for this flow. So if you remember, nonlinear transfer had both blue and red terms here, whereas eddy dissipation is just blue. So that means that it's overly dissipative, which is not a terribly surprising result. And if we look at the error between the eddy dissipation and the nonlinear transfer, that's what epsilon is. So it's very accurate for the 0,4 structure, but it's not particularly accurate for any other structure in the flow. So the eddy viscosity is just a qualitative tool. It's not very accurate quantitatively. It's really only accurate quantitatively for this one scale here. And if I split ed hat into V hat and G hat, I can see that V hat does pretty much all the work. G hat's almost insignificant. So that means that the effective Reynolds number is doing most of the work in this flow for modeling nonlinear transfer. Okay, I promise this is the last gross mathematical slide. So what I wanted to show you now is how the first resolvent mode is always going to struggle to model nonlinear transfer. So I've rewritten this energy balance for resolvent mode. And again, you can just see P plus D plus N equals 0. But what you'll notice is that both production and dissipation have a sigma 1 in front of it. And remember, sigma 1 is the largest singular value. And in some cases, it's quite large. In fact, for cylinder flow, it's on the order of 10 to the 5th. So that's what's pre-multiplying both P and D. N, on the other hand, does not have a sigma. N is literally just the inner product, or if you want to think of it as an overlap, it's the overlap between psi 1 and phi 1. That's what alpha is. And I can actually sometimes write sigma 1 in terms of alpha. So all I want you to take away from this expression is that sigma 1 is inversely proportional to alpha. And alpha is this overlap. So if the overlap is big, that means that these things are the same and they're lying on top of each other. And if the overlap is small, which is typically true for a shear flow, these things are minimally overlapping. And therefore this term is small. So if I substitute this horrible thing into this horrible thing, I get this horrible thing. And I'm going to simplify it to show you that production is proportional to 1 over alpha, because I have a 1 over alpha here. Nonlinear transfer is proportional to alpha, and therefore the ratio of P and N is 1 over alpha squared. So that means that for small values of alpha, P is going to dwarf N. And what we saw for the nonlinear transfer results is that N is roughly the same order of magnitude as P is. So this is sort of incompatible with that observation because it's telling us that the first resolvent mode is going to be so biased in terms of production that it's going to be hopeless at giving us nonlinear transfer. And that means that the first resolvent mode is just not going to be able to get this energy balance. And I'm going to show you that by reconstructing the energy balance with as many resolvent modes as it takes. So what am I showing you here? Well, the solid line is how many resolvent modes you need. And 1 is the final answer. So it needs about 60 resolvent modes to give us the right answer. And the dashed line is how many Eddy modes you need. So Eddy, first pair of Eddy modes does quite well, actually. It gets up to about 0.8, and then it kind of faffs around for a while until it finally converges at about N equals 30. So that's not too bad. That's about half the number of modes that the molecular needs in order to get this scale correct. So it's quite a difference. And it's also worth noting that the molecular one is really slow to get there. And this has sort of been shown also by other authors in a different way, but I'm choosing to show it in an energy balance perspective. So I'm not going to worry about dissipation and nonlinear transfer because really production tends to be the one that slows things down. So I can just show some other plots here. So this is a Spanwise-constant mode. So this is 2, 0. Here, once again, Eddy's much faster than, well, it's not much faster, but it's faster than the molecular. And once again, if I show you even another wave number pair, you'll see that the Eddy is faster than the molecular. So I can actually compare them. So the red means that the Eddy is faster, blue means that the molecular is faster. And what I can see from this plot is that there's kind of a nice division line here, where long structures, so things with a small streamwise wave number and a large spanwise wave number, that means that they're long and thin. The Eddy does a better job here because it's able to get rid of energy that's not, and give it to smaller scales. And the blue does better for short and wide structures. And this T here is just a accuracy threshold. So I said, please reconstruct the budget to within 25% error. The reason I chose 25% is because it looks nice. 1% looks a little less nice, but it gives us the same trends. We can still see that low aspect ratio structures are constructed more efficiently with Eddy modes than high aspect ratio structures. So I think we're all getting knackered here. So this, I'm not going to spend very much time on this, maybe just 5 minutes. This is where we're going to basically have an imperfect Eddy viscosity model to start with, and we're going to say, I can't compute the nonlinear terms for this Reynolds number. I'm just going to try and correct the Eddy viscosity by adding a little bit of information about the nonlinear terms from my available measurements. And I'm going to do this for, I've stolen this from Oniga. This is a schematic that basically shows we're trying to take measurements from one plane and try and infer what's happening on another plane. So her technique used what's called coherence, and coherence is a measure of how correlated a structure is between two heights. So if the structure is tall, you would expect it to be quite coherent over two different heights. But you can also use the Kalman filter, and I'm going to use the Kalman filter today. And this was work done by Illingworth et al. For Reynolds number of 1,000. So what happens at 2,000? And what happens at 2,000, this is a nice DNS field, is that the estimation tends to drag everything down to the wall. So you can see that this structure is quite energetic at a Z of maybe 0.25. But when I look at the estimates, most of the fluctuation activity is happening right near the wall. And that's pretty consistent throughout the whole Streamwise extent of this channel. So the question we're trying to answer, and this uses an eddy viscosity, is why does it drag everything down to the wall? Can we correct that problem? That's going to be the goal of this part of the talk. So this sort of boils down to, once again, looking at stochastic forcing. This is stochastic forcing this time for the Eddy operator. And E just means eddy viscosity, linearized Navier-Stokes. And we can look at the stochastic response for a couple of structures. The first one I'm going to show you is a special case where actually the eddy viscosity almost nails it completely. That's brilliant. You always hope that stochastic forcing can give you the right answer. And if it does, great. You can just go home and eat some chocolate cake or something. And this particular scale, on the other hand, it doesn't do so hot. And the way you can see that is because not only are these different, but -1 is really where the lower wall is. So this structure is energetic at about -0.5, but the eddy gives you something that's really energetic right at the wall. So the stochastic forcing of this eddy viscosity enhanced resolvent, its tendency is to shove everything near the wall. And the reason it does that is because the eddy viscosity profile is small near the wall, and the structure is so damped where it actually is supposed to be that it just wants to migrate towards the wall. It sees all this damping and says, oh my goodness, I don't want to be damped, and it goes to the wall. So what we're going to do is we're going to just stick in another measurement plane at 100. So I'm comparing here what happens between DNS, estimation using one plane at 300, and estimation using two planes at 100 and 300. And Y is the spanwise direction, Z is the wall normal direction. So we're sort of looking at this from a streamwise slice. So you see all these structures. And what you see, of course, is that you have a huge, intense negative fluctuation near the wall here when you only measure at 300. And you can get rid of that when you added another measurement plane at about 100. Okay, so these agree pretty well. I'm cherry picking a little bit because I'm only showing you a wall normal extent of 0 to 500. If I showed you the full channel, what you can see is that I do get some of the stuff happening above 500, but I'm missing a lot of things. And the reason I'm missing a lot of these is because these structures are not coherent with my measurement planes. So coherence is kind of a good way to assess how well can you expect your estimator to work before you even try it. So if these scales are not coherent with the measurement planes, you don't really have much hope in being able to measure them, even with the linearized Navier-Stokes equations. And of course, here is where you get that really intense negative fluctuation of the wall. So I can also show you this in a streamwise wall normal plane. So now we've just tilted the cross section that we're looking at. And we can see that once again, the eddy sort of drags things to the wall, and two planes is able to correct that reasonably well. So I can show you very briefly the error. So the two plane cases really flatten out the error in the log region and some of the buffer region for these large scale structures, whereas the one plane case here, you can definitely see that huge overestimation at 300. And so if I stuck the measurement plane too close to the wall, the eddy viscosity is not able to really give us what's happening above the measurement plane. That's why the error increases quite rapidly. And these are just the same plots, one's in linear units and one's in logarithmic units. The last thing I'm going to show you is that this estimation could improve statistics. So I'm showing you the statistics for a single wave number pair. This is wall normal height on the y-axis, and the x-axis is actually phase speed. So if you remember when I talked about the exact coherent structure, I mentioned that there's typically a continuum of different wave speeds that structures travel at. So for this wave number pair, it's telling you which speeds it's most active, and that's just below 20. And if you look at the predictions from the eddy viscosity, it's actually not bad, but it tends to predict things closer to the wall and at slower wave speeds. So you can see here it's probably about 17, whereas the truth is 19. And if you estimate the velocity field using two planes, you're actually able to correct not only the hugging at the wall, but you're actually able to shift it to the correct frequency contents, the correct wave speeds. So I think I just have one more slide. This is just to show you that the error does really well if you integrate it from 0 to 300. You reduce the error by a factor of at least 3 if you have two planes as opposed to just one. But if you consider the whole channel, for example, the error is not reduced that much because it's just not able to capture those structures in the wake region which are not coherent with the measurement planes. Okay, I think you're all exhausted. I'm certainly exhausted. So as promised, my outline slide is the exact same thing as my conclusion slide. And I just want to sort of reinforce how we dealt with nonlinearity explicitly in the case of cylinder flow. And that's what sort of gave us insight as to why resolvent predictions were slightly different from those of linearized Navier-Stokes predictions. And then we looked at just modeling nonlinearity with an eddy viscosity in part 2. So now you know what these different blocks are. This is the nonlinear transfer, this is the eddy dissipation, and this is the error between them. So it does very well for 0,4, but for the other scales, it's not particularly accurate. And the last thing I talked about was we sort of gave up on modeling nonlinear. Well, we used eddy viscosity to partially model nonlinearity, and then we used some data to try and correct that model. So I'm happy to take any questions in the last 5 or so minutes we have. Thank you for your attention.
Thanks, Sean, for the nice, perfect talk. Interesting. I'll open the floor for questions. Please unmute yourself if you have a question, or type it in the chat. I can read it for Sean to answer. Thanks. No question.
It's okay, I'm used to this after teaching. I think everyone just gets exhausted with the online watching videos all the time.
I actually have a question.
Hi, George.
Hello, Sean. Hello, Sean. I have two little questions. Firstly, on slide 9.
Yeah.
So, yeah, you talk about the fact the resolvent is high rank. That's the resolvent of the 2 omega s, is it?
That's right.
Which is the harmonic then, and then the plot that you have on the left, the different singular values, I like to call it a rankness plot.
Sure.
So that's for a range of different frequencies, is that right?
Yes, I cheated a bit. I should have plotted more frequencies, but yes, this is.
And so one here is that omega s?
Yes, so omega s is just above 1. That's right.
So is it at omega s? Is the resolvent low rank? Yeah.
It is, but the nonlinear forcing is also low rank. So you're right. This is
So
sort of
the white forcing assumption is still not good.
yeah. So the low rank of the resolvents means that it gives you a decent prediction of the structure, but in reality, if you wanted to recover the true structure, it would be best to try and model the nonlinear forcing because it's also low rank. So that's what this is sort of a rankness measure, so to speak, of the nonlinear forcing. So it is low rank at every harmonic of the shedding frequency.
Yeah.
That's right.
All right, thanks. And on slide 11, this is a cheeky question.
Yeah.
How did you calculate your true nonlinear forcing?
Yeah, so that's always a bit of a pain, especially with finite elements. So long story short, I take the velocity field just in MATLAB, have a U, and I just use the gradient function of MATLAB to calculate du dx, dv dx, du dy, dv dy. And then this is nonlinear forcing in the x direction, so this is quite literally just u du dx plus v du dy. And then I calculate that for every time snapshot. And then I Fourier transform it and extract the corresponding bin for the shedding mode.
Yeah,
so
okay. Yeah.
It's a bit like the velocity fields, but I have to pre-compute the nonlinear terms first, and then those are Fourier transformed to get the frequency.
Yeah. Oh, awesome. Thanks. That was a really fantastic talk.
Thanks, George.
I might have also a question, Sean. If
Yeah,
you're
go
going
for
to
it.
your slide 10 again,
Sure.
how the resolvents going to, oh, it's 9, I guess. How the resolvents is going to act when you have two different frequencies which are not harmonic of each other? Is it going to pick both, or is it going to pick the dominant one?
Yeah, that's a good question. So what I've shown you here is sort of an oscillator where you have a very, in a global sense, the flow loves a certain frequency, and then regardless of how you perturb the flow, it will choose that frequency. So I think you're kind of asking what happens in a noise amplifier like situation, like a jet or a turbulent flow, or a turbulent channel, for example. So the resolvent tends to actually be a bit more helpful with identifying energetic frequencies. So in a jet, for example, it'll identify Kelvin-Helmholtz type frequencies, and it'll give you a decent approximation of the structure as well. So the resolvent will be low rank in that situation as well. And that's basically because instability mechanisms tend to get their energy from the mean flow. And if that's the case, then the resolvent will identify that quite accurately. Same with, even if you had two energetic frequencies in the flow. So for example, if I had an airfoil and an angle of attack, oops, sorry. So if this were an angle of attack, I sometimes see two frequencies that are active. I see a Shear frequency and a wake frequency. Both of those show up in the resolvent, actually. I see two peaks.
Okay, thanks.
This is sort of a special case where the peaks don't appear, and that's because these structures don't get their energy from the mean flow. They get it actually from the shedding mode.
Okay.
That's a good question.
Hi, Sean. I've got a question.
Thanks, Julio. Good to see you.
Thank you very much, first of all, for a really nice talk. When you were talking about the coherency between two planes in the channel flow,
Yeah.
you said that the coherency tells you something about the correlation. But isn't it true that coherency, I think if I remember right, tells you about the nonlinearity in sort of a transfer function? So if you've got low coherency, it's sort of telling you, well, okay, it's probably more nonlinear mechanisms are the ones that are dominating. Isn't that really what you're showing? Your coherency?
Yeah, I think I agree with that. Yeah, I think that's true. To be honest, I haven't really thought about it too much. I frequently trip myself up over coherence. Anaga's the coherence expert. But yes, I think you're right. I think that means that your transfer function, I think there was a paper from the KTH group that sort of looked at this, and yes, you would have to sort of take into account a nonlinear transfer function if you wanted to derive the relationship between scales at different wall heights. Yes, I think you're right.
I'm just going back actually to Pendant and Pearsall on random processes. the Bible of them, where they discuss all these things, you know, in the 1967 book, I think it is.
Yeah.
So, where when you're looking at transfer functions and linear systems, actually, I remember something that the statement was that when you have a coherency less than 1, it's saying it's telling you that the system has some, you know, nonlinear effects are becoming quite significant in the system, and they are not being taken into account. That's just, you know, so without something that's recent, it's probably quite old, I think, that kind of stuff.
Yeah, but I think you're right, because I think there was a paper that basically sort of said that and then looked at nonlinear transfer functions. I think they looked at, I think it was sort of a machine learning approach, if I'm not mistaken, that sort of tried to look at the transfer functions, and they were actually able to find quadratic nonlinearities in their transfer function that was able to relate these things better. So I think you're right, yes, and I think there's paper evidence, recent paper, this came out last year, this was Sasaki et al. That looked at this for a turbulent boundary layer.
Okay, very nice. Okay.
Thanks, Julio.
Thank you. Did you have to get up too early today?
No, actually, 6:30 was not bad at all. Normally get up around 7-ish, so this wasn't too bad.
Okay. Thanks again, Sean.
Thank you.
I guess if we don't have any more questions, we might close this session. Some of the people might be interested to go to the next talk by sheer flow people.
That's fine with me.
Thanks, Sean, again for the fantastic talk, and hope to see you face to face in near future. In
Thanks,
the next couple of months, hopefully. And yeah.
Hopefully I'll see you all in some virtual manner at the AFMC.
Yeah. And thanks everyone for attending this seminar, and hope to see you next week.
Yes, thanks everybody.
Thank you,
care.
Sean. Cheers.